Hello, this is Mr. Collier, and today we're going to look at some transformations of exponential functions, and we're going to use GeoGebra to help us. We're going to be graphing these using a slider in GeoGebra. So I want you to open up GeoGebra, and when it opens up, we are going to select Algebra and Graphics, I think will be the best. Maximize the screen. So I don't need the algebra, just the graphics and the input bar on the bottom. That's what you need, the graphics and the input bar. I'm going to put grid lines on so I can read this a bit, and I'm also going to move. I just need the positive part of the graph here, the quadrant 1, I think, and a little bit over here. So I just moved it to this, and I'm going to make a slider called A, maybe from -10 to 10. I think that'll do. So I can make A go all the way up to 10, and that slider is going to help us when we're graphing, so we can change the value of A, so it could be 2, 3, 4, 5. So we'll be graphing y equals a to the power of x in GeoGebra. So down here on the input bar, y equals a to the power of x. Okay, and I graph that, and right now it's just a horizontal line because a equals 1. 1 to the power of any number is 1. You just get a horizontal line there. It's not even exponential. So if I increase a now to go up to 2, then we have the graph of y equals 2 to the power of x. So notice we have some points. We have 0, 1 is on the curve, and we have 1, 2, and we have 2, 4 is on the curve, and then we have 8. So these are the powers of 2, right? 1, 2, 4, 8. The next one's going to be 16. Next one's going to be 32. So if we graph that on our little graph here, y equals 2 to the power of x will go through this point, this one, and then this one. And over here at -1 it's actually half, and then a quarter, and then an eighth. And the curve kind of goes like this. Y equals 2 to the power of x. Okay, so if we change this slider now to go up to 3, here's a graph of y equals 3 to the power of x. Notice it still goes through 0, 1, because any number to the power of 0 equals 1, so we have that y-intercept again. Then we have 1, 3, then we have 2, 9, then it's going to be 3, 27, just the powers of 3, right? So let's graph that maybe in a different color over here on our axis. Again, you have the same y-intercept, but this is going to be 1, 3, and then you're going to go 2, 9 is going to be way up here. And here you're going to have -1 is going to be like a third over here, then a ninth. So it goes like that. Okay, so next we can try y equals 4 to the power of x. Here it is. It goes through 0, 1 again, the y-intercept. And the next point on the line is 1, 4. Then you have 2, 16. So these are the powers of 4. 2, 16, 3, 64. And they get really, really big really quickly. So I'm going to graph this one as same x-intercept. You're going to have 1, 4 is on the line. And here you have -1, a quarter. So it's going to be even smaller there. And it goes like this. It grows even faster. Okay, and the last one, if we do y equals a to the power of 5, still have the same y-intercept because 5 to the power of 0 is 1, and then 1, 5 is the next point, and then 2, 25, 3, 125. Like it's very, very large. So I guess I'll do that one in black. Same y-intercept. Next point is 5, and then it gets very steep after that. So it should be steeper than this green line. It's kind of hard to draw. Y equals 5 to the power of x. Okay, so let's take a look at these instructions as well. Graph each set of functions. Check. Write down the coordinates of the y-intercept. In each case, the y-intercept is 0, 1. Okay. Write down the equation of the horizontal asymptote. Well, the if you go back to here in the second quadrant, the functions are approaching 0, but they never quite reach 0. So that is the asymptote. The asymptote is y equals 0, which is just the x-axis, right? So that is the asymptote right there. Oops, x or y equals 0. So, fourth question. Describe how the graph changes when the constant changes. So how does graph change when A increases? As A increases, you could say, as A increases, you could say the y-intercept stays the same, but the graph, you could say the graph is vertically stretched. Okay, vertically stretched. It's like somebody stretching it out here. Alright, so you can say it's vertically stretched, which means basically that the graph grows at a quicker rate, or something like that. Alright, because they're getting steeper and steeper, so it's growing at a quicker rate. Another couple of examples. Now these are when A is between 0 and 1. So basically a fraction that's less than 1, greater than 0. So we're going to graph a half, a third, and a quarter, and a fifth. So we can do that with a slider very easily by changing our function. Actually, I'm going to use that algebra thing over here right now to get my function. So there we go. So I click on the function. I'm going to change this from A to 1 divided by A to the power of x. Okay, so that way the thing I'll be changing is the denominator of the fraction. So I'm going to do that. And now you see it looks like it's backwards now. So if you get a if you put in a fraction less than 1, you get basically a reflection in the y-axis. Okay, so this kind of function is called an exponential decay function because the values are getting smaller and smaller and smaller. So let's go back it up to A equals 2. So it's the graph of A equals 2. And you can see it looks exactly like the graph of y equals 2 to the power of x, but it's backwards, right? You've got over here, you've got negative 1, 2, negative 1, 4, 8, 16, and so forth. But when you go over here to positive 1, you got half. And then you've got a quarter, an eighth, a 16th, and so forth. Okay, and they're getting much, much, much smaller as x gets larger. Okay, so let's graph that, the first one. Y equals half to the power of x. So again, we had the same y-intercept though, because even half to the power of 0 is also equal to 1. Then half to the power of 1, you get half, quarter, an eighth, 16th, and so on. And this way, to the power of negative 1, you get 2, and then you get 4, and so my curve is going to look like that. That's y equals half to the power of x. And let's try another one now. Let's change the slider over to 3. So here, it looks just like y equals 3 to the power of x, but this is y equals a third to the power of x. It's decreasing as x gets larger, so it's exponential decay again. This is the same y-intercept, the 0, 1. Then we have negative 1, 3, and negative 2, 9, and then it goes 27, and 81, and so forth. So 1/3 to the power of x is going to, again, have the same y-intercept. Then over here you're going to have 3, and then 9 way up there somewhere, and then this is a third, and a ninth. So it looks kind of like that. Y equals a third to the power of x. And I change my slider again. This is y equals a quarter to the power of x. And over here you have negative 1, 4, and over here you have 1 as a quarter. And then that's a 16th, and so forth. So let's graph that one. Again, the same y-intercept, 0, 1. Put 1 over to the left here. the y value is 4. And this should be a quarter. So it's going to look like this. That's y equals a quarter to the power of x. And lastly, y equals 5 to the power of x. Again, same y-intercept, 0, 1, and negative 1, 5 is your next point after that. So that's going to be like 1/5 there, same y-intercept, and go over 1 up 5, so this is going to be hard to draw. It's getting crowded on this graph. That's even steeper. That's y equals 1/5 to the power of x. Okay, so if we answer those same questions before, what's the coordinates of the y-intercept, horizontal asymptote, and describe how the constant changes the graph, we can say, okay, we've already graphed it. The y-intercept is always 0, 1 again. And write down the equation of the horizontal asymptote. Again, it's the x-axis, it's the horizontal asymptote. So that's y equals 0. And the fourth question, how does changing this value change the function? Well, we can say the graph, maybe we can say this, the graph of 1 over a is a reflection in the y-axis of y equals a to the power of x. And I should say over here 1 over a to the power of x. Okay, so the graph of 1 over 2 to the power of x is just a mirror image of y equals 2 to the power of x, right? Okay, next set, we've got y equals 2 to the power of negative x, 3 to the power of negative x. We've got these. So I'm going back to GeoGebra, and I'm going to change my function again back to a to the power of x, but I'm actually going to put in negative x this time. So that's a to the power of negative x. Let's bring our slider down to 2. Now, look at that. This looks exactly the same as y equals half to the power of x. So, and there's a reason for that. When you have a negative exponent, that's the same as that's the same as half to the power of x. Okay, so you just get the reciprocal, and it's to the power of positive x. So the graphs here are going to be exactly the same as what we did in number 2. Alright, so it's going to be exactly the same as the graphs in group 2. Here we have some numbers multiplied by 2 to the power of x. So let's see what the effect is going to be. If I go to GeoGebra, what I want to do is type in here for the function. That's always going to be a 2 to the power of x, but there's going to be some number in front. Actually, let's just call it k. But I think I need to define that first, so actually, hang on now. I need to make a new slider called k. So k, and I will put that between negative 10 and 10 just in case I want to use that. And click OK, apply. Now I'm going to go back to this equation. I'm going to change it to a to the power of x, but k times a to the power of x. Alright. And a, well, we already have it set to 2. K is going to be 2. Alright. So k is going to be 2. So I'm going to bump that up to 2. So what happens when you put a 2 in here is like all the y values are going to be multiplied by 2. So in the previous graph of y equals 2 to the power of x, the y-intercept was 0, 1, but now it's 2 because it's doubled. Everything is doubled. So before we had 1, 2, now we have 1, 4. Okay, so all the points are doubled. So actually, I'm going to graph y equals 2 to the power of x on here first, the parent function. This is what y equals 2 to the power of x looks like. Alright, and then we have this function, y equals 2 times 2 to the power of x. All the points are doubled. So this one was at 2, now it's at 4. This one here was at half, now it's here. So they keep getting halved down here. So what this does is actually it stretches the graph vertically. Y equals 2 times 2 to the power of x. Alright, and similarly, if you've got 3 times 2 to the power of x, we could do that with our slider over here. Bump this up to 3. And you see the new y-intercept is 0, 3. And then the next point here, actually, it would normally be 2. You multiply by 3, it's up at 6, right? So all the points are triple. So this is 3 times a half, you're going to get 1 1/2. 3 times a quarter, you're going to get 3/4. So it's going to look like something like this. Okay, y equals 3 times 2 to the power of x. In this next one, y equals half times 2 to the power of x, so I can make k be 0.5. Well, that's not easy. Let me see. Let's actually just type in 0.5 times that, and okay, we get this graph. So notice the y-intercept now is half, and this number is half. Okay? So the y-intercept is half, and then we have the point 1, 1 and 2, 2. So 1, 1. So if you look at the graph of y equals 2 to the power of x, all your points are half as large. So we have a graph that looks like this. Okay? Y equals half times 2 to the power of x. So it looks like this value of k gives us our y-intercept. Right? So I'm guessing right now this is going to be a third here. Then all the points from y equals 2x are a third down from there. Okay, and it's going to look something like this. Y equals a third times 2 to the power of x. Okay, so what is the y-intercept for each one? Well, the y-intercept here, okay, so I'm going to write down all the y-intercepts right now. The y-intercept here is 0, 2, 0, 3, 0, half, and here is 0, third. In general, it's going to be 0, comma k. It's going to be the y-intercept. And I think, what was the other questions that we have to answer? Write down the equation of the horizontal asymptote. Well, that always stayed the same. Okay, the horizontal asymptote is still the x-axis. That's y equals 0. And what's the effect, or what's the change when you change k? So you could say that k equals the y-intercept. So when you change k, you change the y-intercept. So k equals the y-intercept, and maybe you could say also that increasing k stretches the graph. Alright, so let's take a look at group 5. Now here we have plus or minus a constant. So let's go back to GeoGebra and type in 2 to the power of x plus c. So I'm going to make a new slider called c. Again, let's go from -10 to 10, I suppose. And on my function is going to be 2 to the power of x plus c. Alright, now I think I made a mistake. No, that's right. Alright, so if let's look at 2 to the power of x plus 3. So I'm going to change my slider to 3. Okay, what effect does this have on the graph? Well, there's two things. Your y-intercept is 4, but actually the whole graph is the same as y equals 2 to the power of x, except all the points are up 3. So the graph is shifted up 3 units. Okay, so for y equals 2 to the power of x plus 3, everything's shifted up 3 units. So that's going to be half, quarter there. And actually, I think I made a mistake there. Yeah, so normally y equals 2 to the power of x, your y-intercept is 1. Now it's shifted up 3, so it's going to be up here at 4. So this is half, quarter, an eighth. And we have a new horizontal asymptote here. It's going to be up here at x equals 3. Alright, so let me actually write that in there. So there's the horizontal asymptote at x equals 3, and this is the graph of y equals 2 to the power of x plus 3. Alright, and we do the same thing for the slider and bring down c to be 1. Then the whole graph is shifted up 1. As you can see here, the horizontal asymptote is y equals 1. Yes, y equals, not x equals. So y equals 3 here for the horizontal asymptote. For this graph, the whole graph is shifted up 1. So it's going to look like that. That's y equals 2 to the power of x plus 1. And for minus 2, you can guess what's going to happen. If I change the slider to minus 2, then actually I'm going to move the graph now and just check it out. The y-intercept is normally at 1, but now it's down 2. The axis of the asymptote is normally at y equals 0, now it's at y equals negative 2, so it shifted the whole graph down 2. Alright, so it looks like it's right here. So that's the graph of y equals 2 to the power of x minus 2. And 2 to the power of x minus 1 shifts the whole graph down 1. And the horizontal asymptote is right here at y equals negative 1. And for the green line, it's at y equals negative 2. So if we look at the y-intercept for each one, the y-intercept for the first one is 0, 4. So it's actually 1 more than the c value. The y-intercept for the next one is 0, 2. The y-intercept for this one is 0, negative 1. And the y-intercept for this one is 0, 0. Okay, so if we look at part 3 is write down the equation of the axis of symmetry. The axis of symmetries are going to be y equals 3. It's going to be the same as the c value, right? So y equals 2. Y equals negative 2. Oh, that's right, that red one should be y equals 1. And the last one is y equals 0. So the axis of symmetry is equal to c, whatever c may be. Okay, so that's part 3 there. And the last question is, what does the effect of of changing the constant c have on the graph? Well, we can say that c is, I would say y equals c is the equation of the axis of symmetry. Okay, we could say, and we say for the transformation, the value or the graph is translated or shifted C units vertically. Alright, so if C is 3, the whole graph is shifted up 3. If C is negative 2, the whole graph is shifted down 2. So that's how you describe the transformation there.